Okay, good morning, everybody. Welcome back. Happy Monday. Today, March 6th. Project number 4 is officially assigned. Go ahead and grab one from the table. You are able to do, after today's lesson, you'll be able to do a bunch of this project, but there's still going to be a little bit at the end of the project that we don't yet quite have the tools for. We will develop the tools before the project is due, which is 1 week from today, March 13. You're going to want to try to do what you can on this project early so that at the last, like the last couple of days of the project, you're only working on the newer stuff, which we haven't yet seen. Today and next class, we're going to talk about improper integrals. Quiz number 4 is going to be due coming up on Friday. I'll hand it to you on Wednesday. Questions on the schedule? When is what? It's due Monday. Yeah, project is due Monday. Other questions? Okay, so here we are at the top of page 18. An integral with an infinite interval of integration. Let's just pause. That's a lot of words. For example, this guy right here, an infinite interval of integration. In this case, integral from 1 to infinity. Right? That's something we have not seen. Next century. How about that? Or an interval with an infinite discontinuity within the interval of integration. You can stay where you are, but take a look at this integral right here. Integral from 0 to 1 of the square root of 1 minus x. What happens when I plug 1 in for x? You get division by 0. This is the graph right here. At x equals 1, this thing blows up to infinity. So that's an infinite discontinuity right there inside of that interval of integration. When you get either of those kinds of things, we call that integral an improper integral. Improper integral. In this section, we learn how to deal with such beasts. Please remind me to encourage you to verify your answers on the calculator. All right, let's give this a shot. Suppose we want to find this integral from 1 to infinity of 1 over x squared dx. Part A, what does this integral represent? Here's the graph of y equals 1 over x squared. We know the definite integrals represent area, so let's shade in that area from where to where? From 1 to forever to the right. So this area is what we are trying to find, okay? That area is what we are trying to find. All right, so here is my question to you, just like an instinct kind of question. Is this total area equal to 1, 1,000, 1,000,000, or infinity? We're going to the right forever. There is positive area to the right forever. So every step you take to the right, you are adding more positive stuff, and you are doing that forever. I haven't done this one out all the way, but I'm pretty sure the answer is one of those 4 things I've written up there. Do we have a gut instinct? 1, 1,000, 1,000,000, infinity. A couple of votes for 1. It goes forever. It goes forever, so your vote is infinity. That's a reasonable thing, isn't it? You're adding positive stuff forever. Feels like the pile should grow to infinity. All right, let's take a look. Part B says first we're going to find the integral from 1 to b of 1 over x squared. B is going to be just some generic finite number. Let's find this thing right here. Okay, integral 1 to b. This is really x to the negative 2 dx. And then this is our power rule. Add 1 to the power and divide by the new power. X to the negative 1 over negative 1 evaluated from 1 to b. You're welcome to plug in now, but I would first rewrite that x to the negative 1 so it's a little bit more friendly. Everyone agree? That's really negative 1 over x. Okay, and so now we're going to plug in the b, top and bottom. Plug in the b and the 1. So negative 1 over b minus negative 1 over 1. Okay? Plug in b, plug in 1, subtract. All right, we're going to rewrite this just a tiny bit. Minus minus makes a plus. I'll write the 1 first, and the minus 1 over b second. Okay with that? Okay, so if you are going from 1 to some generic number b, the area under the curve is 1 minus 1 over b. So if I had just sort of put b here at some arbitrary spot, then this area from 1 to b is 1 minus 1 over whatever that magic number b is. What do you think we want to do with b to get a sense of the value of the infinity integral? Well, we can't plug in infinity, but what can we do? We take a limit as b goes to infinity. That's what we're going to do. So here we go. This thing here equals, leave a little space, integral 1 to b, 1 over x squared dx. And in that space, limit as b goes to infinity. Makes sense. So we can put in any finite number we want for b, and then we're just going to send b to infinity. That's how we deal with that issue. Okay, this thing here equals, copy that limit one more time. And then instead of that green integral, what did we discover? It's really 1 minus 1 over b, right? That's what we found for the original green integral there. It is 1 minus, let's see here. So as we send b to infinity, this thing right here goes to what number? Goes to 0. So 1 minus 0, which is 1. So the area under that curve approaches 1. As
it's always getting smaller, so it's never going to get large enough to cancel out or to add to the smaller area under 1 until like, some smaller number, but not anywhere near infinity. Really small. Never going to account for that. It's a fraction.
Yeah, so it feels like, the curve that we were looking at here is going to the x-axis really, really fast, right? And so it's true, even though we're adding more and more positive stuff, we're adding these little like tiny fractions of whiffs of hardly anything. And so even as you add all this to the pile, it turns out the pile never gets bigger than 1, approaches 1. Sadly, there are other curves which look an awful lot like this one, where the answer is infinity. The difference between 1 and infinity is just not as big as you might expect. So this guy right here is just 1. Let's use the calculator. You can do this if you want, but you don't need to. But let's test our answer here. Math integral. The function is 1 divided by x squared, comma x, comma 1, comma. Okay, so now we're going to pick a number. I can't type infinity here, but I can type in any finite number I want. For example, 10. The integral there is 0.9. Okay, that makes sense. Should we have known it was going to be exactly 0.9? Remember the 1 minus 1 over b? 1 minus 1/10. Hey, 0.9, of course. All right, second enter. So if I did, for example, 1,000, 1 minus 1,000th, 0.999. You guys are faster than a calculator. Look at that. That's pretty impressive. And the idea is that, like the bigger the b you put in, the closer that guy gets to 1. It's never going to get equal to 1, but it will get as close as you want to 1. So we define the integral to be 1. Okay, so we defined this integral, a to infinity, to just be the limit as b goes to infinity of a to b. Right? Just send b to infinity. If you had a minus infinity at the bottom, change it to an a and take a limit. Right? So any infinities, you just change to a letter and take a limit. If the limit exists, like it did in our case, we just got 1, then we say the original integral converged to 1 in this case. But if the limit is infinite, we say the integral diverges. So converges or diverges. Next page. Now suppose we want to find this integral, 0 to 1 of dx over square root of 1 minus x. All right, so I've given us the graph here. Let's shade in the area that we're interested in. This was the area from 0 to 1. So it starts there and goes all the way over here. And in this case, the issue is that x equals 1 because the function blows up, right? Gets infinitely large up there. So where is the problem? X equals 1. How are we going to fix the problem? We're going to change it to a letter. So for example, integral from 0 to b, and then what are we going to do with b? Limit as b goes to 1. Okay, let's give this a shot. So part B. Evaluate integral from 0 to b of that same exact integrand. So this thing here equals, okay, first let's rewrite this guy. Integral 0 to b of 1 minus x to what power? Negative 1/2, right? Square root, and it's on the bottom. Okay, equals. All right, this is basically just the power rule. We're going to add 1 to the power and divide by the new power. So 1 minus x to the, when you add 1 to the power, 1/2. When you divide by the new power, it's going to be a times 2. I'm going to put a divide by 1/2 right here. And then this thing is evaluated between 0 and b. That said, I was a little bit too cavalier there by just saying add 1 to the power and divide by the power. That's only good if it's just x to a power or u to a power. But this is a u substitution. Are you looking for the calculators? They're still in my office. That's a u substitution. What should we have let u equal? 1 minus x. What's the derivative? Negative 1. And that negative 1 we did not account for, and we need to account for it. So I'm just going to put it in a different color here and say negative that thing, and then say do the whole u substitution process. Right? It's a whole thing that we did not write out. But you got to be careful. Anything other than x or u, you really should write out the details. Okay, let's clean this thing up before we plug in the 0 and the b. Okay, so you said it was 2 in the front. I'll throw the negative in the front there as well. And then 1 minus x to the 1/2 is really a square root. So before I plug in my b, I always like to make the thing we're evaluating as friendly as possible. Okay, so then it's just a simple matter of plugging in square root of 1 minus b minus square root of 1 minus 0. I've done something kind of funny. I actually don't think I've talked about this in this class, but that negative 2 I put in the front with parentheses, as opposed to maybe the more common thing would be to treat the whole thing right here as one expression, and you plug in the b and you plug in the 0, and the negative 2 would be in both. Personally, I always factor my constants out in the front. I just think it's easier. Okay, so we've got our answer here. What we really wanted was the integral from 0 to 1. What should we send b towards? 1. So we send b towards 1, and let's give that a shot here. So this thing equals limit as b goes to 1 of what? Oh, thank you. Okay, so we're just going to send b to 1 in the thing that we just evaluated up there. Okay, so what happens? Equals negative 2 parentheses. We're sending b to 1. Well, we can just plug b equals 1 in right now. Let's do that. Square root of 1 minus 1. And then outside of that is a minus 1. What is that equal to? 2. That's our answer. So it turns out that area, even as there's this vertical asymptote at x equals 1, turns out that area that we shaded in at the top is exactly equal to 2. Nothing more, nothing less. Okay, so new vocabulary. Did that original integral converge or diverge? Converged. We got something finite. If we got infinity, we would say it diverges. What does it look like when you get infinity? I'll just show you real quick. Suppose that this had been a 1 divided by that square root. 1 divided by that square root. 1 divided by 0 diverges. Stop right there. Okay. All right. Okay, so number 5 is really informal. When the interval of integration contains an infinite discontinuity, you just replace the discontinuity with a letter and take a limit, just like we did. Number 6, how would we approach this integral right here? We're not going to do the entire thing. We're just going to set this one up. That integral, dx over x minus 2 to the 2/3 integral from 1 to 4. So what's the issue with this integral? Why is it here in this section? Yeah, at x equals 2, this thing blows up, right? You imagine the graph of this thing. It's going up to infinity at x equals 2. And so we've got this infinite discontinuity right in the middle. And so if you were to just, if you didn't recognize that 2 was an issue and that 2 happened to be in between 1 and 4, and you just do the u substitution, you will get an answer. And it will be the wrong answer. Like you cannot just assume that like the integral is going to yell at you at some point if you miss the fact that 2 is a problem here. So this is one more thing you're adding to your list of responsibilities, is that for definite integrals, you better make sure that the integral is well behaved in the entire interval. Okay, but how would we set this one up? Well, that integral has the problem at x equals 2. What we need to do is split this into 2 integrals. Integral from 1 to 2 plus the integral from 2 to 4. I'm going to start getting lazy here and not rewrite that integrand. So I split it up. We know that we can just split the integral anywhere and just add up the 2 pieces. 1 to 4 is really the same as 1 to 2 plus 2 to 4. And then in the first one, we're replacing the 2 with maybe a b, and we'll take a limit as b goes to 2. And then I'm going to be lazy, plus the other one. How about we pick a different letter down here? Can we go a to 4? You're welcome to use the same letter, but typically a is on the bottom, b is on the top. And this one, a goes to, also goes to 2. Okay, so you'd split this, 2 separate integrals, 2 separate limits. If they're both finite, then the integral converges, but if one is infinite, the integral diverges.
You don't have to do this from the left or from the right.
Yeah, if it, sometimes it does matter. In this one, we would approach 2 from the left because this was the integral from 1 to 2. And here we'd approach 2 from the right. Oftentimes it makes no difference, but if it does make a difference, then yes, put in the plus or minus.
Does it not make a difference?
I don't think there's anything we can do to resolve the problem in this case. I don't think it matters, but you can play around with it. Okay, improper integrals, there you have it. The activity is on the next page. I will walk around.